For number 1, we're given a relation as a set of ordered pairs, and the first thing we're supposed to find is its domain and range. So remember, domain is just the x values, range is just the y values. So for part A, it's just a matter of listing the x's, which are -3, 0, 0, and 0. And remember, we don't have to list the same value more than once. So we can just say the domain is -3, 0. And then the y values for the range are 2, -4, -5, and 1. So just putting those in increasing order to make it look nice would be -5, -4, 1, and 2. And then determine if the relation is a function if it does not identify two ordered pairs as proof. So remember, in order for a relation to be a function, we need all of the x values to be different. And we do have repeated x values here, which means this is not a function. And where do we see the repeated x values? Well, we've got an x value of 0 getting paired with 3 different y values. So we could give any 2 of those 3 points as proof that this is not a function. So we could say 0, -4, and then 0, -5. For number 2, we're given a graph, which is actually the graph of a parabola, graph of a quadratic function. And for part A, we're trying to determine if this graph is a function. So we said for this one, what we were looking for was, do we have a repeated x value? Now graphically, as in number 2, if we're trying to determine if something is a function, this is where we apply the vertical line test. And if we lay a vertical line on top of that graph, no matter where we place it, it's only going to hit the graph in one place at a time. So that tells us that yes, this is a function. We could say that's because it passes the vertical line test. And then determine the domain and range of the graph in interval notation. So domain, this is where we're asking ourselves how far to the left and then how far to the right does this graph go. And remember, those arrows on the ends tell us that it keeps on going forever. So the domain of this graph is going to be all real numbers, or in interval notation, -infinity to infinity. And the range, we're looking up and down. How far down does this graph go? And then how far up does this graph go? So down, again, those arrows tell us that it's going to keep on going down forever, all the way down to -infinity. But going up, this graph does have a highest point, which occurs at -4, -3. So this graph takes on a highest y value of -3. So that tells me that my range would be everything from -infinity up to and including -3. Number 3, we are given the function g of x equals -6x squared minus 6. And we are supposed to find g of x minus 1. So remember what this notation means. This is telling us that whatever we see inside the parentheses, which in this case is the x minus 1, gets plugged into this function everywhere we see an x. So we're going to replace this x with an x minus 1, which would look like -6 times x minus 1 quantity squared minus 6. And then this is one that, because we only have an exponent of 2, is not that difficult to simplify. We just need to FOIL x minus 1 times another x minus 1, which would give us x squared minus 2x plus 1. And then we still have the minus 6 on the end of that. And then we can distribute the -6 through the parentheses to get -6x squared plus 12x minus 6. And then bring down our other minus 6. And then combining these constant terms on the end would give us -6x squared plus 12x minus 12. And this would be our final answer. Number 4, we're trying to determine the domain of the function f of x equals the square root of x plus 8 minus 3. So this is a square root function. And remember, we said the thing that we need to watch out for with our square root functions is that we're not plugging in anything for x that would give us a negative number underneath the square root. Or in other words, whatever's under the square root, in this case that x plus 8, we need to be at least 0. We need it to be greater than or equal to 0. And then to solve this inequality for x, we just need to subtract 8 from both sides. And that tells us x is greater than or equal to negative 8. So we can only plug in numbers that are at least as big as negative 8 into this function. If we plug in anything smaller than negative 8, that is when we will end up with a negative number underneath the square root, which we can't have. So this would be our answer. Then just writing it in interval notation would look like bracket negative 8 to infinity. Number 5, we're doing the same thing, except now we're given a function with a denominator, negative 7 over x plus 5. And we said the thing that we need to be concerned about with our denominators is they can't be 0. We need to make sure that we're not plugging anything in for x that will give us a 0 in the denominator. So in other words, we need to figure out where that denominator of x plus 5 is equal to 0, which subtracting 5 from both sides tells us that x equals negative 5 is what would make that denominator equal to 0. So that tells us the one number that we need to throw out from this domain. That's the one number that we cannot plug into this function. And remember, when we had just a single number that we were trying to throw out of our domain, what that looked like in interval notation was negative infinity to negative 5, parentheses, union, parentheses, negative 5 to infinity. That's how we show that we're excluding just the number negative 5 from all real numbers.